Hello, this is our ME 401 final presentation on the topic of the FEA discrepancy factor for 3D printing. A little background on this topic. FEA, or finite element analysis, is one of the most commonly used techniques for evaluating 3D designed components. Specifically, SolidWorks and the integrated FEA through SolidWorks is taught in the curriculum to Clarkson students. FEA on 3D printed parts is incredibly unreliable at this time. If it is used, it's very time and resource intensive and requires a significant design skill set, which most college students don't currently possess. Gyroid is a infill pattern. It is one of the most commonly used in engineering applications and is the most requested infill pattern at the Dwarf Makerspace. And the Clarkson Mini Baja team is looking to use more 3D printed parts in our yearly design competition, such as the possibility of a steering wheel. But as the competition is design oriented, we need to make sure that our components will hold up and will be as good, if not better, than their steel or aluminum counterparts. So our actual objective is to develop a modulus equation that we can use to create a new substitute modulus that could be used in SolidWorks in a custom material profile to more accurately get results from the FEA based off of what infill percentage you're printing your component at. This is all assuming that you're using the gyroid infill pattern. For a quick overview of our experimental plan, the main variable we're planning on changing is infill percentage. We will be testing 5 different infills, 5%, 25%, 50%, 75%, and 99%. We were unable to do 100% because at that point there is no pattern to be seen. So looking at gyroid infill at 100% isn't possible. So we will just be going up to that 99%, and the same goes for the lower limit of you can't have 0% because then there would be no pattern at all. As for our controls, we're planning on keeping the print settings consistent throughout our different sample prints. The first is the printer model, so all of these samples will be printed on a Prusa Mark III. The filament will be a Prusament black matte PEPG. The number of walls will remain 2, and the infill pattern will remain gyroid throughout all of the samples. So with any experiment, there is obviously risk involved. The two main sources of risk in our experiment are from the 3D printers and the load frame. So for the 3D printer, there is the risk of chemicals. So as it's printing, it releases vapors and chemicals into the air. The Dwarf Makerspace, where these are being printed, has a ventilation system and an enclosure system for their 3D printers. So this is a pretty minimal risk. Especially as with the hours of the makerspace, you can't stay in there for the extended periods of time that would cause some sort of 3D printer related illness. The second risk with the 3D printers is the high temperatures that they operate at, which can be a risk of burning. The best way to minimize this risk is to wait for the 3D printer to go through its entire cooling cycle before removing the prints. It does have a notification when that is completed and it's safe to remove the prints. So make sure we're awaiting that entire cool down cycle to avoid that. And there's moving components as the printer is printing. So just not interacting with the printer more than the designated interface while it is printing. If there is some sort of issue, get the makerspace staff or press pause and then wait for the proper cooling to occur and then the movement to stop before trying to interact with the sample. As for the load frame, there is the risk of flying debris. As you're doing a compression test, the sample could always come dislodged and move out from underneath the load frame. In order to minimize this, all of the participants in the experiment were wearing safety glasses while the machine was moving. And again, there is a moving components pinching and crushing risk. So before the machine is operated, it was verified that all the participants had their um, hands and just themselves away from the machine. The experimenters were informed on where all of the emergency stops were before continuing with the experiment. So for the budget of this experiment, the costs are very negligible considering that all of the materials that are required are already free and accessible to clerks and students. So the cost of the 10 3D printer samples comes out to be about 40 cents in total, since each is about a gram and a half of filament. And the student budget for the makerspace uh, over covers this amount, so that cost is negligible. Um, the actual load frame itself is quite expensive to buy initially, but there is one in the mechanical engineering lab that we are able to use. And um, for the 3D printer to actually print the samples, um, those are also decently expensive, but the Dwarf Makerspace has access to those, and so we were able to use those without any additional charges. As for the equipment and materials required for this experiment, the a load frame is required. In this case, we are using an Instron 430i, a 3D printer. In our case, we are using the Prusa MK3s, and the actual sample test blocks themselves, which we decided to create using PEPG.
All right, so first I'm going to talk about the experimental procedure for this project. So the very first step, which is actually not on here, we're going to calibrate the 4301 instrument load cell first to make sure everything's clear, nothing wrong with the machine. It gives us the correct codes. Now, the first step in actually running their test is to set the speed of the load frame to 0.05 on the machine. Then the second part is to mount the sample and put the holding blocks into the load cell. Then the third is to twist the load cell fixture to 2 rotations counterclockwise. Then, using the manual jog buttons, move the fixture down until it just is a little bit above the sample. So it's not quite touching it, but it's really close. And then the next step is to twist the counterclockwise the top plate until the the two plates and the test piece itself are in contact with each other. Then zero the load frame in that position, and then you start running the compression test on the blocks themselves. Then, as that compression test is going, you will be recording at intervals of 0.005 inches of displacement until that load frame nears the 200 pound force limit of the machine, so you're not breaking the machine. And then, after you record all the data, you return the load frame to its original position up above, and stop it there. And then you repeat from steps 2 to 9 with each new sample that you have for each different infill, and just keep going until you get all the data that you need. This is an image of our test piece here, or test setup. So I'm just going to mark it here. So right here is your top plate. Here's your bottom plate. Then in the center here is your work piece that you put in there. So the first thing is to use the is to twist that top piece that I initially marked, which is right here again, and you twist it until it fully in contact with your workpiece, and then you run it through your simulation, and it will crush the part, not fully, but it will deform it just a little bit, obviously. But that is our testing setup that we have.
Quick note on the next two slides. When we sent this from PowerPoint into VoiceThread, there was an error with something with the text size that moved some of it behind the images that we weren't able to figure out how to fix. So I just want to apologize for that in advance. For our data analysis, we plotted the load measured versus the extension for each sample, and then constrained our analysis to the linear range of that data, which ended up being about 0.02 and 0.06 inches. A trend line was created for each of those samples, and then the slope of it was recorded. That slope is in units of pound force per inch of extension. So we used the area and length of the sample to convert that into a strain per stress, which would give you a modulus. And then we compared that modulus to the modulus of the 99% infill case to give us a correction factor, which is essentially a fraction of the initial or a fraction of the modulus based on the infill, which you can see on the right, which actually had a very strong linear relationship with a very high R squared value that we can feel pretty confident about. We then used this correction factor to see if SolidWorks was able to properly predict the deflection of a compressive load. So we took the initial modulus and applied that correction factor to get a corrected one for what would be a non 100% infill material that with whatever infill we wanted to run. We ran that for a couple of cases in SolidWorks where you just place a load, evenly distributed load on the top, and you set a boundary condition for no movement at the bottom. Then we applied the same load that we had measured at the load cell and then recorded the deflection or the displacement of the top. The results for this were a little unexpected because they were very consistently at about 0.03 inches of deflection. They hovered a little bit around there. The table on the right, you can see it ended up rounding a little bit. But it was actually relatively consistently around 0.03 inches, which is really interesting because that is not what the load should be at, because each load measurement that we ended up inputting into SolidWorks was recorded at a deflection of 0.05 inches. So something is wrong with our methodology here. And the consistency of how wrong it is showing that it's likely an issue with our methods and not like random error or small mistakes. This could be a couple of things. First thoughts are whether or not our method of zeroing the location on the load cell was correct, because if we were consistently, off by a little bit there, that could result in this. It would have to be something with our setup, most likely. We also considered that it may be the angle of the plates of the load cell, which were not always perfectly parallel, which made sort of setting it up perfectly every time a little tricky. The other potential solution is that this is just not a robust way of doing analysis, I suppose, where correcting the modulus before running the SolidWorks analysis, something like in the FEA makes this a problem that isn't just like a direct correlation. So our conclusions are a little bit that unfortunately this is not a suitable method for any sort of project where you need any amount of accuracy.
In conclusion, the method utilized went through multiple different iterations to reduce error as well as safety concerns operating the load frame, but ultimately the error of our final solution was still relatively high, around 38%, but that was different in each trial. Um, Coming from this, we can assume that there was some error associated in the surface area on the top of 3D prints, as 3D prints have relatively loose tolerancing on final parts, and the size of our final parts were small enough that we probably needed to seriously worry about the surface area discrepancy between testing samples, as well as that um, the there was many difficulties using the machine itself. The manual was helpful, and we eventually ended up calling tech support to try and help us with some other issues we were facing. But we believe that there was a lot of error associated with zeroing the load frame exactly, as it appears a entire control panel or readout display was missing from the machine, according to the manual, and could not be located, meaning the experiment could be performed, just not to the level of accuracy that we would have wished we could have had. Coming from this, accurate analysis for infill is nearly impossible without significant time and computational power. Throughout this experiment, we tried multiple times to get a better computational model to display infill, and we're unable to without significant time investment, as 3D prints have walls and an infill percentage, and this is extremely hard to model, especially when it comes to gyroid, which is a 3D shape that is somewhat helix-like. It's extremely difficult to model and to work with. Future work. First thing that comes to mind in future work is a change in test sample. Our first design and test sample was very flat and not very tall. We could not get accurate readings off the load frame due to its low accuracy near zero. Upon talking to Professor Hoover, we decided to come up with a taller test specimen that was thinner, which performed a lot better, but the surface area was so small that we ran into 3D printer tolerancing issues. So if this experiment were to be performed again, a intermediate solution would be best, something that is tall but a little wider to prevent some of those tolerance problems. A recent feature we discovered in when it comes to printing is the no walls feature as well. So walls on 3D prints are not counted into infill percentage, meaning when you are testing purely infill percentage, it's another variable that is constant throughout all the 3D printed samples, but based on heating conditions of a nozzle or things like that, could affect test data and could be another source of error. If we were to continue with this experiment, a change in equipment would be important. Um, the load frame we were using, we believe, was missing a instrument slash readout panel that could have been extremely helpful in eliminating error, especially when it came to zeroing the machine. Also, familiarity with the machine. This was the first time we used this load frame, and there is some inherent error in learning how to use the equipment while you're doing an experiment. Even though plenty of background research and reading was done, there could be a possible error there that could be corrected in future experiments. Change in sample size is something that is needed as well if this were to become a extremely accurate experiment. So more samples per infill and more samples at different infills. It would be nice in a perfect world. There would be 10 to 20 samples of each infill percentage going from 1% to 99, um, giving us a great view of how infill directly affects modulus, which probably would significantly reduce error, as we would have a very wide swath of data to pull our numbers from. I wanted to quickly acknowledge Professor Carl Hoover for helping us diagnose our error early on in this experiment, as well as helping us switch between our initial experiment topic revolving around Baja hubs to the steering wheel, as another load frame we were planning on using was having mechanical problems and electrical issues that could not be remedied in time for the experiment's conclusion. I also wanted to shout out the Dwarf Makerspace staff who have been nothing but supportive to this project and let us explore various tools and technologies that we could use to create a overall better experiment. Namely the no walls feature, which we believe would be instrumental to this experiment if it were to happen again. And Robert Davis, the speed coordinator, he allows us to do what we do at Baja, and there would not be this experiment if there wasn't a, uh, a Baja team at Clarkson.